tools, and he's going to talk about entanglement as an organizing principle of quantum mechanics. Please take it away.
No, thanks a lot. It's a great pleasure to be here again after 5 years. I think 5 years ago there was a very similar conference here in Liverpool. It was like the very first conference after COVID, so everybody was super happy to come here, and I still remember the fantastic atmosphere. That's why I'm really glad to be here and to report on new developments in the field of tensor networks. So I know that somehow most of you are probably not physicists and are not too familiar with tensor networks, and that's why for talking with Jacob, I decided to give a very general talk. But at the end, it will become much more focused on actually tensors and the theory of tensors. So to start with, I just want to briefly go back. Of course, the previous talks already kind of touched upon this, but on the quantum many-body problem. So basically, quantum physics is exactly 100 years old. 100 years ago, we had the Schrödinger equation, and Dirac immediately realized that because we have the Schrödinger equation does not actually mean that we can solve all problems in physics, because solving the Schrödinger equation is a problem that is exponentially hard in principle. It has an exponential scaling in the number of particles and the number of the number of tensor products. It has a tensor product structure, and therefore there's an exponential scaling in the number of parts in this tensor product. And indeed, somehow, if you look back at the history of quantum physics, theoretical quantum physics, in most of somehow the big breakthroughs were like ways of circumventing this exponential wall. So let me kind of try to give some examples. So Hartree-Fock is by far the most successful kind of was the first application of quantum mechanics to the many-body problem, and it's effectively saying, let's reduce this problem of working in an exponentially Hilbert space by working on a variational manifold of Slater determinants, which is an exponentially small kind of set of states, because Slater determinants only have a number of degrees of freedom that scales polynomially in the system size. And by restricting yourself to this manifold of states, suddenly you could do many-body physics. You could start understanding chemistry. You could start understanding material science. So this is basically the very, very first big breakthroughs involved. And then you say, okay, for some systems, this is not enough. This variational manifold is not capturing some of the physics that I want. I need to also do some perturbation theory on top of this. And this is what is called Feynman diagrams. So these Feynman diagrams are just a way of organizing some perturbations on top of the Hartree-Fock ground state. And so you can even do this in an extensive way. This is now what is called coupled cluster theory. This is like by far somehow state of the art of dealing with interactions in quantum chemistry. But of course, there's many other things. Like density functional theory is also like a way of circumventing this exponential one. Yeah, but turns out that many strongly interacting systems of interest do not have somehow a good Hartree-Fock state to start from. You cannot kind of use, there's no somehow Slater determinant on which you can start doing perturbations, because all the Slater determinants have basically completely negligible overlap with the exact state. So this is what is happening, for example, with the Hubbard model. That's why for things like the Hubbard model, these methods are of not many use, especially in the regime when U is large. There is no good fiducial state to start with on which you can do perturbation theory, and that's the difficulty somehow in the many-body problem. And this is something that is a regime that is actually very relevant for many problems in material science and in physics in general. Yeah, and then there's not that quantum Monte Carlo methods they can help, but in many cases of interest, there's something like a sign problem. Okay, and this is there a problem? But this is, of course, somehow the premise of a quantum computer. So the quantum computer should then basically be able to solve this. This is the main application of quantum computers are envisioned to solve this many-body problem. So this is envisioned that indeed for problems of interest, you will be able to use quantum computers to actually solve or at least simulate the many-body problem. And of course, this asks the question, is this really so? So what is the difficulty? What are somehow the problems, these many-body problems that we care about? Where are there special features there that we have not thought of, that can be exploited to come up with much more efficient? So we wrote a paper like something like 15 years ago. So it's called the convenient illusion of Hilbert space. It turns out that all the states that we care about. Okay, so actually, if you have the full Hilbert space with this exponential scaling, turns out that all ground states and thermal states of local Hamiltonians actually live in a very tiny corner of that Hilbert space. And the whole premise or the whole framework of tensor networks is built on trying to identify very special properties that the states that live in that corner have. Okay, so you have to identify that there are special features. If you have a ground state of a system, like you have a Hamiltonian, a many-body Hamiltonian, what is so special to ground states? Well, just because you're mathematicians, one of the very first things that is interesting to think about ground states, if you have a many-body ground state and you're taking your system, you're taking the limit of the system size going to infinity, well, typically there's only one state that is an eigenstate of this Hamiltonian that is renormalizable. Okay, all the other states are actually not L2 normalizable. Yeah, all the other states are scattering states, they're excitations, they're kind of all the eigenstates are delta normalizable. There's only one state that is L2 normalizable, or there's two, there's the ground state and the highest energy state. Okay, that's already very, very, very special. Okay, so there's many special features that these ground states have that we can exploit. And this is exactly what we are trying to do. So what is the main property that actually has not been proven yet rigorously in many cases, but somehow this is what physicists does not kind of prevent physicists to kind of take this as a starting point. This is namely that there's very few entanglements in ground states. So actually, if you're interested in these eigenstates that are normalizable for a many-body Hamiltonian, there's actually very, very little entanglement in the system. So if you kind of take, for example, a two-dimensional system and you take some region of it, you take the ground state of this and you kind of take certain region and you calculate the von Neumann entropy of that region, it will be something that scales like the boundary of that region, not like the volume of that region. And that's what is called the area law. So that means that all the entanglement in a ground state is then somehow concentrated somewhere around this boundary. Okay, so this really suggests that there should be a completely different way of representing wave functions. Instead of working with the full Hilbert space, you should actually think about how this part interacts with the other part. You should think about correlations between different systems, between somehow system A and B. You should kind of think about how to route, how the entanglement basically can be, how the entanglement can be described between the different system sizes. And indeed, this has been proven rigorously for things like one-dimensional quantum spin systems, and also been proven rigorously for Gibbs states that you have in area law. There's still lots of interesting mathematical questions about what happens in two-dimensional, not just quantum spin chains, but like two-dimensional versions, three-dimensional versions. But somehow for most of the problems that we care about, there is some strong evidence that this area law is actually true. So that if you have a Hamiltonian with a gap, that means that even if you kind of if the system size goes to infinity, the difference between the first excited energy state and the ground state energy does not go to zero. That means that you have a gap system. Then we strongly believe that the ground state will satisfy an area law. Okay, and then the question is, how can we take advantage of this? How can we actually understand or model the wave functions in such a way that you would automatically have this area law scaling embedded in the variational constants? And this is all about entanglement. It's about how do you model the entanglement in these many-body systems. Okay, so let's start with something very simple. Let's start with a Heisenberg antiferromagnet. So I have two spin-1/2 systems, so two qubits. Okay, they interact via the Heisenberg Hamiltonian. If you have two spins, then the ground state is just singlet. Okay, spin up, down, minus, down, up. This is the unique ground state of the Heisenberg antiferromagnet for two spins. If you have three spins, it's already very difficult. It's much more difficult to do the exercise. So we can try to figure it out. And indeed, what it is, you have a singlet. There's an up here, minus singlet between these things, and this is one of the two ground states of this system. So you see, it is kind of, it's really difficult to guess how things work, but what you see at work here is the monogamy property of entanglement. So you would like any two spins, you have a spin chain or a spin system satisfying or governed by the Heisenberg Hamiltonian, you want the ground state, you would like that all the marginals of the nearest neighbor spins are as close as possible to the ones of the singlet, because this will obviously minimize the energy. But you cannot do this. If the spin 1 and 2 are in a singlet, then the third one has to be completely disentangled from it. And obviously, if you have a symmetry like this Hamiltonian is symmetric, like you have the ring, and it has to be translation invariant, the marginals have to be translation invariant. There will always be a ground state that will have the symmetries, inherit the symmetries of your, at least the ground state subspace will inherit the symmetries of your Hamiltonian, and therefore you also must have translation invariance. And that's why these strange properties come out. So it's what you start seeing as a competition. It's a competition between symmetries and entanglement. And whenever you have competitions, you get something interesting. This is why statistical physics is interesting. It's a battle between energy and entropy. Here it's a battle between symmetries and entanglement. You want to have a symmetric system, you want to have translation invariance, but you also want to have as much entanglement as possible. And that is this monogamy of entanglement. And indeed, these tensor networks or some matrix product states are exactly the solution to scaling this up, to this, trying to understand how can I construct a system of on a chain with, let's say, even a thermodynamic limit, such that all my nearest neighbor spins are very much entangled, but I still have translation invariance. A naive case would be, okay, let's take a singlet here, a singlet there, a singlet there. Obviously, this is only translation invariant if you shift over 2. So what are these matrix product states? They basically say, well, my physical degree of freedom is actually some combination of these two. So these are like these blue dots, these maximally entangled states. So these blue dots are maximally entangled, but my physical degree of freedom is only living in a subspace of these 2 degrees of freedom. So I have a maximally entangled state, a chi-dimensional maximally entangled state between these two, but then I say my variational degrees of freedom will be how is my physical Hilbert space related to this squared dimensional Hilbert space. So you just put some linear map that maps these chi times chi Hilbert space to, say, a 2-dimensional Hilbert space, and you do the same thing everywhere, then automatically your system will be translation invariant, and automatically you will have lots of entanglement between nearest neighbors. Okay, so this is exactly, you write this out, this is exactly giving these matrix product states that we heard about in the previous talk. So this is the physics intuition where this is all coming from. Yeah, this AI indeed, so this I index is the physical index, and these alpha and beta, so these are the virtual indexes, can be much, much larger than the physical index. It turns out that this is a very interesting object from a mathematical point of view. So you see in this case, you even define it in a thermodynamic limit. You take the same tensor everywhere. So turns out that this matrix product state manifold is a low-dimensional Kähler manifold. So has both a complex and a symplectic structure. You can actually do study the metric parallel transport. Something like very famous is the fundamental theorem of matrix product states, has to do with gauge invariance. So, but anyway, the really important property is that this manifold is in one-to-one correspondence with all ground states of gapped quantum spin systems. Okay, so if you have a state on that manifold, there is actually a Hamiltonian for which this is the ground state. And vice versa, taking any local Hamiltonian that is gapped, there will be a matrix product state that is in some sense very close to the exact ground state. So that solves the problem of characterizing ground state of quantum spin chains in one dimension. So this was a big deal. It's a very big deal because it reduces the problem of trying to understand ground state physics to that of studying the properties of a manifold. A low-dimensional manifold is in one-to-one correspondence with all ground states of local Hamiltonians. And of course, because you have this symplectic and this complex structure, you can do things like TDVP, the time-dependent variation principle that we heard about before. These were all things that we worked out, let's say, like 15 years ago. And you get very interesting nonlinear differential equations. So you get very interesting and very useful methods for simulating this. And indeed, somehow it turns out that by generalizing this to higher dimensions, you can now very easily do this. Once you have this picture of how to model states that satisfy an area law in a systematic way, like in 2 dimensions, you want to have lots of entanglement between all neighbors in all directions, but you also want to have the same symmetries, the translation invariance. Well, you just take the same principle. You take a tensor here with 4 virtual legs, 1 physical one. You project all these things down. So it means that whenever you have a leg that's connected, you sum over this index. This system will be translation invariant, will have lots of entanglement between nearest neighbors, and will satisfy an area law with respect to any cut that you will take in the system size. So this is the very natural generalization. And so we see that 2-dimensional physics is full of loops. There's loops everywhere. And that's why these things gives rise to much richer phenomena in 2-dimensional physics than in 1-dimensional physics, because you have all these extensive amount of loops, and you will have to deal with this. If you don't do this, you do not capture the right physics. and also other kind of methods that have been developed. MERA, the multi-scale entanglement renormalization ansatz, you can build other structures that have some intrinsic scaling that are very well suited for describing critical systems using the very similar techniques. But anyway, the crucial point is that you can characterize now ground states of many body wave functions in this exponentially large Hilbert space with just one tensor. You have this one single tensor that characterizes basically the ground state of the whole system. So that means that the properties of this one tensor, the symmetries, all the kind of properties that this tensor have, will have some physical meaning. And indeed, different phases of matter will correspond to tensors with different symmetries. So you reduce the global problem to a local problem that has to do with the properties of a single tensor. And that's why I think this fits, of course, very well within the scope of this tensor conference. Okay, so it's all about studying properties of tensors. Okay, so let's physics point of view, there's lots of interesting properties or not lots of interesting concepts that emerge by looking at it this way. So these tensors model the entanglement structure. So modeling correlations makes much more sense than modeling the wave functions directly. Okay, so this is somehow the fundamental insight that we are basically understanding or trying to dictate the entanglement patterns in the system. Depending on what the geometry is of your system, you have to use a different ansatz. So these tensors can be, turns out they can be efficiently counteracted due to some holographic property. So it turns out that even these two-dimensional cases, although in principle these could be very hard problems, these could be anti-hard problems to contract these tensor networks. In practice, they are not. In practice, they turn out to be very simple to contract. That's why you can come up with variational methods based on these tensor networks. Okay, so you can immediately define these objects in the thermodynamic limit. So there's no kind of real scaling. There's no, it's fine because there's some uniformity kind of properties of these things. So this means that you can immediately kind of study systems in the thermodynamic limit in the infinite space because there's this one tensor that you just repeat infinitely many times. And then instead of doing finite size scaling, which is one of the main methods to study critical systems in physics, you can start looking what happens if I do finite entanglement scaling. Okay, this finite entanglement scaling is something that is when you increase the number of variables in your system. Okay, the number of variables was related to these maximally entangled pairs, this variable chi. You increase this, you get more variational parameters, and you can now variationally minimize the energy with respect to this chi and then extrapolate and actually get a perfect scaling laws and study critical systems in an amazingly accurate way. I think from the theoretical point of view, the most interesting part of this tensor network description is that you have a completely new way of characterizing phases of matter. Instead of having to talk about Hamiltonians and ground state of these Hamiltonians that are very difficult to characterize, you can just look at the symmetries of the local tensors. And if you kind of go from one phase of matter to another phase of matter, this will be completely reflected in the fact that the symmetries of these local tensors will change. And this also includes the case of topological order. We will come back to this later. Okay, so for the high energy people in the audience, so this tensor networks really realized a dream that Feynman had. So Feynman, for a big part of his life, was trying to, at least that's what he said, try to come up with a variational method for doing quantum field theory. And he always failed. There's several reasons why he failed. But then he gave a very interesting talk, one of the very last talks that he gave. People asked him, what do you really think that we have to do to kind of get this done as variation? And he says that we have to surround a certain region with an object, or the region that we want to calculate by a surface, and describe what things are coming in across the surface. It tells us everything that's going on outside. So we have a certain region, and the only thing that you care about is the correlations between this region and the outside region. And that's exactly what these virtual degrees of freedom, these tensors, deal. They tell you the degrees of freedom, the symmetries of these. Okay, so let's now focus a little bit on the computational aspects of this. So it turns out that these tensor networks explain the humongous success of something that's called the density matrix renormalization. So this is this paper of '92 by Stephen White. So he derived a completely new method out of the blue to simulate quantum spin systems. And this immediately reduced this exponential complexity problem to polynomial complexity problem for simulating ground state of quantum spin systems. So this was like an amazingly and completely unexpected. So he did this using a very complicated reasoning in terms of density matrices and RG methods and all these kind of things. It turns out, and this took 10 years for people to understand, that this DMRG is nothing but a variational method over the set of matrix product states in which you use an alternating least squares method to solve it. So you have like a tensor network, you have all these different tensors, and DMRG can be understood. This is what we realized when we started looking at this. It's like you fix all these tensors but one, minimize the energy of your Hamiltonian with respect to one tensor that you vary. This is a quadratic problem, and then just go back and forth like in an alternating least squares method. So this is what DMRG is. DMRG is an alternating least squares method over the variational manifold of matrix product states. Okay, so but it's amazingly successful. Like there are kind of problems also in statistical physics. So 2D statistical physics is very, very similar to 1D quantum spin chains. So there's indeed this mapping, this Euclidean mapping. You can map a quantum problem to a classical problem by doing the Euclidean path integral. That's why statistical physics in 2D is very similar in complexity to quantum physics in 1D. And one of these very famous problems is like the hard square model. So the hard square model is like I have a square, and if this square is filled, then I cannot have any filled squares around it. The question is, what is the entropy of the system? How many configurations can I have on a square lattice when I take the lattice size going to infinity? Using these methods, this was actually just some bet that I had with somebody. We did this, and using this DMRG methods, you can actually get 58 digits of precision for this kind of problem. So this is completely unheard of, and this is actually not a very complicated calculation using matrix products. And just to exemplify how incredibly precise these methods work, this is in the thermodynamic limit. So this is converging extremely quickly. Okay, so the computational point of view, what has been extremely useful is to look at these tensor networks from the manifold, from the manifold point of view, from the tangent space point of view, like related to the talk that we saw at the previous talk. So what we realized is that this NPS forms the scaling manifold, and you can understand or optimize or come up with novel optimization algorithms by, for example, evolving your wave functions in imaginary time. Instead of evolving in real time, you evolve your wave function in imaginary time, then you will always evolve to the ground state. Because in imaginary time, you have an exponential suppression of all the higher energy states. Do this on these manifold, take into account that you have some curvature, all this, work with the right gauge, and then suddenly all these things can be done independently. So you can actually do much more. You can also study, for example, scattering. Okay, so this is something that was left as an open problem, I think, in the last talk. What happens if you take two of these excitations and let them scatter, and you have the ground state? Like you can start actually scattering magnets, calculate S matrices. This is using the double tangent plane. You can still kind of do all these calculations, and this is what we did. We calculated indeed the scattering properties of this. So you can actually also start formulating all these methods directly in the continuum. Okay, so these tensor networks are not limited to describe quantum spin chains. You can actually come up with a field theoretic version of this, in which your degrees of freedom are not just anymore the spins, but are somehow some fields. And you reduce the problem of finding ground state of quantum field theories in 1D to the problem of identifying generators of some Lindblad equation. And using this, you can actually really start looking at the quantum versions of the Gross-Pitayevsky equation. It turns out that, like, for 1D systems, and this is of course very appropriate to talk about this here, the Gross-Pitayevsky equation is like the Bond dimension 1 version of MPS. Okay? So, and of course, this works in the continuum. And now you can ask, what happens if I also allow for entanglement? Using this continuous matrix product states, you can really kind of start looking at this and optimizing this, and indeed seeing that indeed in 1D, you absolutely need to take entanglement into account to get the right physics. Okay, there's also like two-dimensional versions of this. This is, like, I already talked about the PEPs, like this two-dimensional version. This is also like 20 years ago when we started looking at this. You can start optimizing this. This was turned out to be much more complicated, because it's not just a very simple alternating least square method does not really work. You have to be much more inventive. And in the last 10 years, actually, there has been lots of progress in optimizing these PEPs, wave functions, using especially automatic differentiation techniques. So Turns out that using this, we can start solving really interesting problems, like the Hubbard model. The Hubbard model has been one of these open problems in condensed matter physics for a long time. Well, we are getting very, very close to completely being able to solve this by variational methods based on these tensor networks. Yes, so, but of course, we can do things more. We can also look at, again, two-dimensional quantum physics is very similar to statistical physics in 3 dimensions. Exactly, again, because of the Euclidean path integral approach. So like a very long-standing open problem was the residual entropy of spin ice. Okay, so I have to take ice and I cool it down to absolute zero. It turns out that there's still entropy because there's many, many configurations that have the same energy. And Pauling at some 1.5, and then people have been asking since then, what happens if you take interactions into account? If you don't do the mean field thing, and at the end we were able to solve this using these answers and got how these free energy exactly. But of course, we can also do quantum systems like Shashi-Bertrand model. Like Philip Corbos is one of the persons who is the most active in and is really the world expert in optimizing these steps wave functions for interesting problems like Shashi-Bertrand. That is actually also realized in the lab. There are like dispersion relations. So this tangent plane IDs that were discussed in the previous talk, they also work in higher dimensions. They work in 2 dimensions. You have to be a little bit more careful in how to label this, but you can get dispersion relations. We get quasi-particle energies in the 2D Hubbard model and so further. Okay, so one of the main features that is interesting in these numerical methods is that what happens if you simulate a critical system. Okay, so for a critical system, these matrix product states are not meant to work. So what happens if you have a critical system and you approximate this with a matrix product state? Effectively, the system will add a relevant perturbation to the system and will simulate that perturbed system that has a gap. And this is, but that means that, and this perturbation gets smaller and smaller the bigger you make the bond dimension. That makes that you can do entanglement scaling methods. These entanglement scaling methods, as a function of the bond dimension, you can plot, for example, the magnetization as a function of one of the correlation, like that C is a perfect fit, and you can extrapolate. So the fact that matrix product states always are in one-to-one correspondence with gap systems is actually a feature instead of a bug. It's exactly because it opens a gap that you can get much more precise results for critical systems. If they would also be able to simulate critical systems, would be much worse off than being able to do this finite size scaling or this finite entanglement scaling, which looks contradictory, but it is actually the way it is. Okay, so can also do chiral spin liquids. This was another kind of big open problem that was only solved very recently. Like, can you actually deal with chiral spin liquids? Can you capture this with these tensor networks? Because there's some there are some no-go theorems, and there's some very interesting theoretical results still that turns out that if you make the bond dimension bigger and bigger, the system becomes less and less critical because chiral spin liquids indeed are gap systems, and if you simulate them using tensor networks in 2D, actually you get critical systems because 2D tensor networks can be critical. But the larger you make the bond dimension, the less critical they become. So you get inverse scaling laws. This is still an open problem of how to deal with this. And a recent, kind of very recent version of this was actually just published this year, where you also can look at fractional Chernin. So also there, these PEPS wave functions seem to be able to capture everything. But of course, there's much more than just this MPS and PEPS. There's also multi-scale minimization group ansatses. It's called NERA, tensor minimization group, TRG, TNR, loop TNR. So this is something, the whole field, a different way of capturing effectively the same idea that entanglement is the thing that you need to capture or to simulate or to circumvent the many-body exponential wall. Okay, so using this tensor networks, people are actually already looking at QCD. So this fact that these tensor networks will be able to do something non-trivial for actual QCD is not that far off. Okay, so of course we are not competing at all with the QCD groups because there's like thousands of people, of groups in the world that have this completely optimized quantum Monte Carlo code for QCD, but still baby versions of this QCD can already be done using this tensor networks, and it seems very promising that we will be able at some point to kind of get there too. Okay, so another part of this whole research in tensor networks is actually there to simulate quantum systems. So it turns out that all the quantum supremacy claims, so there have been many that you probably have seen in the news, like Google that claimed, oh, we have like a quantum computer, we did a calculation with this, and it will take on the biggest, the fastest supercomputer in the world, it will take at least 10,000 years to replicate this result. Well, then there's some Chinese people that using a laptop effectively kind of did this in half an hour. Okay, and this, of course, they use tensor networks to simulate this. Okay, so tensor networks are effectively giving you a way of solving problems that people thought would be impossible to solve. Okay, so this all quantum supremacy claims from all companies have actually been debunked by using these tensor network methods, these numerical tensor network methods. So they have to kind of push this charter. So of course, at some point, quantum computers will be able to do things that you cannot do with tensor networks. I don't think anybody believes that you will be able to come up with a factoring algorithm using tensor networks. But maybe they will need much bigger numbers before they somehow will be able to be competitive with this. So maybe there are actually good ways of using tensor networks to come up with much better ways of factoring large numbers. Okay, but I think from the audience here, the mathematicians, the most interesting part is probably not just the computational aspects, but rather the theory. And the theory of tensor networks goes hand in hand with the characterization of phases of matter. So this is the most exciting, from my point of view, part of theoretical physics in the last 20, 30 years, is somehow the idea that we have to revisit what phases of matter are. Okay, how do you characterize this? How do you understand this? So the first person to actually understand phase of matter or to think about this was Pierre Curie. So Pierre Curie had this amazing insight that phases of matter are characterized by groups. So you have to study group theory to understand phases of matter. What he said is that symmetries are only interesting if they are broken. Okay, so indeed, different phases of matter are basically can be understood in the ways in which different groups can be broken into subgroups. Like you have a continuous group, maybe this becomes a finite group, that this is how you characterize different phases. And Landau built onto this to basically understand or to do this in the quantum version. He said that gap phases are effectively labeled by the broken or the unbroken subgroups of the characteristic symmetry group of the Hamiltonian. These are the different ground states or the different ways in which you can have phases of matter. And phases of matter are really kind of understood in terms of if I'm one phase, there's no nice adiabatic way to go to another phase without crossing a phase transition. At some point, something has to kind of go crazy. Maybe you get an infinite correlation length, you get all kind of properties. Because indeed, a symmetry, you have it or you don't have it. Okay? There's an index associated to a certain group. If we have a subgroup and another subgroup, if I go from one subgroup to another one, there's something discrete that happens. So there's not something continuous. They cannot go continuously from one subgroup to another one. That doesn't make sense. There's an index associated to this. And that's why phases of matter can be characterized indeed by something subgroups. Okay, but it turns out that many phases of matter cannot be just understood in terms of group theory. Yeah, and this is why Sagan went together with many other people starting in the 80s, started thinking about some generalized Landau paradigm. So what this is about is that gap phases of matter are actually characterized by their entanglement structure, not just by the symmetries of the system, of the ground state, but actually how is the entanglement distributed in the system. And this is, of course, exactly what these tensor networks are meant to do. Okay, so these phases of matter, this is probably one of the very first really kind of interesting cross-fertilization kind of things that happen between quantum information and quantum computing and condensed matter. It's trying to understand or to define very precisely what a phase of matter is. So basically what you can say is that two gap Hamiltonians with the same symmetry or in the same phase, if there's a symmetry preserving a adiabatic path, interpolating between them without closing a gap. Okay, so basically it means that if there is a sublinear, so you have a ground state of a system and another ground state of a system, these two ground states are in the same phase if there's a quantum circuit that maps one to the other one with a depth that is sublinear in the system size. Okay, if you turns out that this is the right way of defining phases of matter. And of course, what we already kind of talked about is that these tensor networks, certainly for 1D systems, they span the manifold of ground states. And because of Landau and Curie and Sagan once said it's about symmetries. Well, obviously, it's very reasonable to conjecture that phase transition will happen exactly when the symmetry of the underlying tensors change. That's exactly what will happen. Okay, so for this, we have to study symmetric tensors. You have to just look, I have a tensor with 3 legs. What does it mean to have a symmetric tensor? Well, very easy. This is effectively what we call, in physics, we call this the Wigner-Eckert theorem. Tells you that any tensor with 3 legs that is symmetric under some kind of a group has to be effectively can be represented in terms of Clebsch-Gordon coefficients. Okay, that's it's a linear combination of Clebsch-Gordon coefficients. These are the only objects that are symmetric with respect to a sun. Yeah, this is the Wigner-Eckert term. I don't know how it's called in mathematics, but certainly I think this is the first instance of these kind of claims was good in physics. Okay, so it's about symmetric tensors. Okay, so of course you can have two ways in which somehow you get symmetric tensors. Either you have also a physical action, so you have like some representation of a group and V minus one, and all of these things together are symmetric. So this tensor is invariant under a certain group. So this is, for example, this could be spin 1, this could be spin 1/2 and spin 1/2. All these things can indeed fuse to 0. That means that there is a Clebsch-Gordon coefficient that is associated to fusing two spin 1/2 to one spin 1. Okay, that's its symmetric tensor. But this is not the only way in which you can get symmetric tensors. You can also have symmetric tensor purely on the virtual way. You can have a tensor that is invariant under multiplying left with Vg and Vg minus 1, where V is the representation of a group. Okay, it turns out that tensors of this kind will represent symmetry broken phases of matter. Okay, so it turns out that this ground state will be reducible. Okay, if you have an NPS of this kind, you will be able to write this NPS as a sum of other NPSs. Okay, but if this is not the case, then you will not. And that which is effectively like what means to be symmetry breaking. Okay, so it turns out that these things are much more interesting in 2 dimensions. 2 dimensions, you could ask, what is the analog of the Wigner-Eckert theorem? So you could say, yes, sure. If I have a tensor that is symmetric, it means if I act on my physical leg with something, I act on the virtual legs with another thing. And indeed, if you just make a full tensor network with these properties, you will see that, of course, it is invariant under acting with Vg, because this leg will cancel this leg if you connect them. This Vg will be cancelled by Vg minus 1 of some other tensor on top of it. This means that your whole system will be invented with global UG symmetry. So this could be a conjecture that this is the most general way in which I can write down symmetric tensor networks, but it turns out that this is not the case. Okay? The most general way in which you can write down symmetric tensor networks is something that if I act here with a symmetry, then there is an other tensor. Okay, this is now a matrix product operator. This green thing actually has also entanglement there that I can put through. So this thing times UG is equal to this thing. And indeed, you can easily kind of imagine that if I have tensors with that symmetry, then my wave function still has a global symmetry UG, because I just have a green thing that I pull through. It will kind of create, like from right to left, it will kind of act with UGs on my physical legs. You pull around the torus, this kind of green line disappears, and you multiply it all your physical UGs with UG. So this is a much more general way in which you can have symmetry. And it turns out that this is exactly what is needed to understand topological order in 2-dimensional quantum spin systems. Yeah, this is a very fashionable subject because this is exactly what is needed to understand quantum error correcting codes. Quantum error correcting codes turn out to be in one-to-one correspondence with topological phases of matter. And topological phases of matter are actually the ones in which you don't even have any physical action. This is a purely virtual action. This UG is just the identity, and you pull this through, and this will kind of be invariant under this. And these green lines are, of course, also tensors. So there's this Vg is now a tensor with 4 legs. This will form another algebra. Okay, so it turns out that if you kind of look at these, because this is symmetry normally for normal symmetric tensor networks, where this is described by a group, then I will have that this green NPO times this NPO is this pumpkin. And if this line is there, if this green line has a bond dimension larger than 1, people in physics call this an anomaly. Okay, so anomalous symmetries are the ones that are described by symmetries of this kind, where this green line is not just one-dimensional, in which this is not a tensor product, but it's an entangling tensor product. What I do here is connected to what I do there. It's not just a normal tensor product. Okay, so again, as I said, these purely, like the really kind of interesting cases are the ones in which the symmetry is purely virtual, so there's no action on the physical leg. There's only virtual actions. These, again, are called Wilson lines. And if you have this, because there's no physical action, there's no reason anymore that actually, if I multiply one of these and another symmetry, that this has to give rise to unique symmetry. Okay, there's no kind of rule. There's no something like Wigner's theorem that tells you that symmetries have to be represented using unitaries. And now, because this is a purely virtual symmetry acting on this entanglement diffusion theorem, the only thing I need is that I have the associativity structure. Okay, this NPO times this NPO has is a linear combination of other NPOs, and this n has to be independent of the system size. So you basically keep the axioms of a group, except that you don't request that if I multiply one simple object with another one, I get a unique other object. You still need to have an inverse and all this, but if I multiply two, I can have a sum of magnitudes. So the defining property of a group, namely the associativity, is still there. That's why it's extremely restrictive. But to understand symmetric or phases of matter, you will have to understand basically the ways in which these symmetries can be represented. Okay, so that means that actually to understand topological order, we have to redo this whole idea or this whole reasoning of Curie that said to understand phase of matter, we have to look at subgroups and look at all possible ways in which groups can be represented. We now have to do the representation theory of fusion categories. Because it turns out that objects that have a property like this with an NABC that is are related to fusion categories. Okay, and these fusion categories, certainly as a non-mathematician, are extremely kind of difficult to penetrate. No? So of course, I bought this book, Tensor Categories. I don't understand much about it, but turns out that if you have 10 minutes, yeah, if you understand tensor networks, you don't really have to understand too much about it because we immediately start. Tensor networks will allow you to do the representation theory of these fusion categories. So it's probably very difficult for the mathematicians and the audience to understand, but as physicists, we don't care too much about groups. We care much more about the representations of groups. And this is how we think about groups. It's much easier to think about, like if you think about SU2, it's a very abstract object, but if you start thinking about 2x2 matrices with determinant 1 and they are unitary matrices, that's something that is actually very easy to deal with. Yeah, this is, of course, a representation of the group. In the same way, these fusion categories are something very abstract to deal with. Yeah, there's all these very abstract axioms that define them. But if you start thinking about how do I represent them, then it turns out that these matrix product operators or these tensor networks are exactly kind of the language needed to do this. So it was a very complicated process to understand this. So basically we worked with the mathematicians like Jürgen Fuchs and Christoph Schweigert to understand the connections and to develop the full representation theory of fusion categories. And just to kind of show you the difference in the way we represent this. So this in this book that I kind of showed you before of Ettinghoff, what is written there is that philosophically the theory of tensor categories may perhaps be thought of as a theory of vector spaces or group representations without vectors. Okay, that's exactly what mathematicians like. Okay, and then what we wrote in our paper, I really had to fight with Jürgen and Christoph for this. Pragmatically, the theory of matrix product operator symmetries may therefore be thought as a theory of vector spaces and group representations without vectors, with vectors. Okay, so this is, we start kind of doing again the representation theory of fusion categories. And this is exactly done using these MPO algebras. So what is this classification? How do you kind of come up with all possible representations? Okay, so for a given category, what you have to ask the question, what are the possible modules that are compatible with it? So for example, for a group G, the fusion category. So the normal group theory is like you start with the fusion category where the simple objects are just the elements of the group. Okay, that's a valid fusion category. It's a very simple one, but still this is allowed. You ask, what are the possible modules compatible with this? Turns out that they are in one-to-one correspondence with the subgroups and or basically the cosets of the subgroup and a two-cos cycle. Okay, there's a mathematical fact that is well known that you can find in this book. And then it turns out that because you have a module, actually C is a left module, C acts on M, automatically because somehow you request that this module is invertible, turns out that there's a dual category that emerges. Okay, and this dual category is actually typically the representation theory of this. So if H is equal to G, okay, this means that M only has one simple object. This is called VEC. Okay, so I take just my subgroup H to be G. Okay, that means that my module is just this theory of vector space. Then this is nothing more than the usual representation theory of groups. And on the right-hand side, what I get then is rep, let's say, of G. And the rep of G, okay, the representations of a group also form a fusion category. Okay, so for example, take SU2. If I take spin 1/2 times the spin 1/2, I get a spin 0 times a spin plus a spin 1. Okay, this is this NABC, is basically it tells you if I fuse this with this, I get a sum of other things. So this is the general way, this is all the complete way in which this works for symmetries. And it turns out that these MPO algebras allow you to do this for any fusion category. You can find all possible modules for a given fusion category and represent them using MPO algebras. Okay, so how do you do this? Well, it turns out that these NPOs have some hidden structure. Okay, so all these lines, not only this is one line here, but this is the virtual degree of freedom. It turns out that you have to separate, you have to get some more refined version of these NPOs in which every line consists out of a triple. Okay, so every line in this tensor network now becomes a triple and consists out of a label N, a label C, and a label N, and a label M, D, and M. Okay, and what you have is this bimodule structure that C acts on N and gets again a module, but D also acts on M on the right-hand side and gets the other M. Okay, so this gives rise to some tensor, and this NPO symmetry can be represented using something like this, and this gives generalized basically representation. So these two F symbols, the thing that we call 2F, or effectively these NPO symmetries, for a normal group, these objects correspond to the EREPs of your group. Okay, and of course, what you have once you have this, you also get some Clebsch-Gordan coefficients. What happens if you fuse two of these objects? I can take one of these things to this, there will be some Clebsch-Gordan coefficient in this direction. There's also a Clebsch-Gordan coefficient in the other direction. And all this kind of data that you get by generalizing the representation theory of groups in terms of these bimodules can be completely captured in terms of these NPO algebras. Okay, so this is exactly explicitly what happens if you have an NPO and another NPO and they form a representation of a fusion category. That means A times B must be a sum over C's. There is an object that you can pull through that will basically intertwine this A, B to C. Okay, you kind of do this on a ring, this object will disappear, and this is basically finding invariant subspace. The same thing in this other direction. Have a dual fusion category. So like this would be the fusion category of the group elements. This would be the fusion category of the EREPs of the group. Okay, so like this would be spin 1/2 times spin 1/2 is a 0 plus 1. And this would be just nothing more than the group elements. Okay, so what turns out that once we started doing this, we came up with some generalized Wigner-Eckert theorem. Okay, any tensor that is actually invariant under such an NPO algebra has to be able to write it in terms of these generalized Clebsch-Gordan coefficients. And indeed, all symmetric Hamiltonians are of that form. So we can really kind of develop the whole theory and actually come up with new theories, new CFT. It turns out that these NPO algebras, these generalized symmetries, are symmetries that are also very much present in 1D critical systems. If you look at conformal field theories, these fusion categories are very much part of that theory. Turns out that fusion categories and physics came together when people started looking at symmetries and CFTs. But using these formulas, we can now look at fusion categories that people have never understood or never found in CFTs and construct new wave functions, new kind of Hamiltonians, and look at the CFTs, and we can construct new kind of CFTs that were unknown. And actually, this is still a completely open problem what these CFTs exactly are. Okay, so what is also very interesting and very relevant is that these different representations, okay, so these different representations are all about what are the possible modules compatible with a certain fusion category. If I take one module and I take another one, let's say R and Q, then it turns out that you will be able to find intertwiners that act on your Hilbert space that map operators in one realization of your theory to the dual realization. And people that are familiar with statistical physics or high-energy physics, they have, of course, heard a lot about dualities or gauging. It turns out that both gauging and dualities kind of are completely captured by this. You have a certain system, you have a dual realization of the system with different degrees of freedom. There is an intertwiner that maps anything from one theory to the other one. And all these dualities, certainly for 1D systems, can be understood in terms of these NPOs. Okay, so, what is interesting is that the dual symmetry is typically categorical. It's 2 minutes. So if you have like an SU2 symmetry, then the dual theory will actually have a rep SU2 symmetry. That means that the symmetries are not anymore like just tensor product symmetries. They are symmetries that are given by these NPO algebras. They are anomalous symmetries. That's typically what happens there. And therefore, excitations will get string ordered parameters. All these things are completely captured by these NPO objects. Okay, so what about the phases of matter now? Okay, so said that the different phases of matter are characterized by different ways in which the symmetries are represented. And phase transitions happen when these symmetries change. Okay, so what we talked about is the symmetric tensors. We had an NPS tensor. If this NPS tensor turns out to have a virtual symmetry, this is an NPS that corresponds to a symmetry broken GHG long-range order state. Okay, but you could also have like a projective way in which this is realized. This was spin 1/2. This is like spin 1, spin 1/2, spin 1/2. this is actually something that also has an anomaly because the group SU2 is not equal to the group SO3. And that's why you get an anomaly again. You get somehow a non-trivial phase of matter, this sign that cannot be changed adiabatically because a sign is somehow there or not, you cannot change this continuously. Okay, that means that SPT phase and quantum spin chains are completely characterized indeed by somehow the symmetries of these tensors. Okay, but let's actually recall the classification of bimodules. Okay, so symmetries, so it means that symmetries of tensors are basically characterized by subgroups and co-cycles. Modules of categories are characterized for categories that are given by VEC of G, so the group, but the simple objects are just the group elements, are characterized by exactly the same objects. Although these are completely different questions. No? The one question is how do I characterize symmetries and symmetry breaking? And the other one is how do I classify all somehow the representations of a certain symmetry? Okay, in principle, these are completely different questions. Okay, but it turns out to be not a coincidence at all that the same data is needed to classify bimodules and different kind of symmetries. It turns out that every 1D Hamiltonian is dual to a unique Hamiltonian where all dual symmetries are completely broken. Okay, so this is actually a very non-trivial result. It tells you if I have a quantum spin chain with a certain symmetry, okay, a certain phase that is a symmetry that's not broken or whatever, there is actually a dual description of the same Hamiltonian where all the dual symmetries are broken. Okay? And this turns out to be a much more efficient way of representing these wave functions than the original one. Because if you don't have symmetries, it means that there's no redundancy anymore in your description. Okay, so the bond dimension of this dual theory will be much lower than is completely broken, or which the symmetries are broken, has a much lower bond dimension than actually the original theory. And this is why the state-of-the-art DMRG methods they make use of these fusion categories. Okay, so instead of studying the original theory, you go to a dual description of the same theory where there's no symmetries left and the bond dimension is much lower. Therefore, you need much less degrees of freedom to kind of capture the same physics. This is just an exemplifying, like the Schmidt coefficients. Depending, like you take an A4, A4 is of course a very famous group, and there turns out to be 7 different modules for that group, seven different kind of subgroups and co-cycles, and then you can study all the 7 dual theories and look at the entanglement spectrum for these 7, and you immediately see that, for example, this one is the most efficient of these, at the least Schmidt coefficients and has a much more efficient description. So that means that every theory is dual. Okay, so maybe let me actually, well, it turns out that the full representation to understand complete spin systems, you have to understand not just one bimodule, but you have to understand 3 bimodules. Okay, so the one about representations was basically this bimodule. The one about dualities is about this bimodule, but then it turns out if this is a bimodule and this is also a bimodule. And this turns out, this module that you get here is actually the one that captures the entanglement degrees of freedom of your system. But I'm very happy to talk more about this if people are interested in. One thing that I didn't mention that is very important is boundary conditions. Okay, so this is something that it took a long time for me to appreciate. If you say that you understand a quantum spin system and you study a quantum spin system and you understand that, you should understand it with respect to all possible boundary conditions. And the boundary conditions of a quantum spin system are actually something that are one-to-one correspondent with something that's called the tube algebra. This is a very famous object in fusion categories. This is the so-called Drinfeld center. That is the one thing that is in common to all dual categories. If I have a certain category, I have a dual category, they will have the same Drinfeld center. And that's why boundary conditions of one theory will be mapped to boundary conditions of another dual theory. And for everybody that has seen things like Jordan-Wigner, you know that this is very tricky. You have to be very careful with boundary conditions and charge sectors and how all these things are matched. Turns out that these Drinfeld centers are the ones that completely explain this. Okay? And if you do this, you can actually lift all these symmetries to unitaries. So you can actually go back to the whole idea that all symmetries are realized by unitary circuits. Okay? These non-invertible NPO symmetries are actually unitaries if you take boundary conditions into account. And this is something that is very interesting. That means that many people call these NPO symmetries non-invertible symmetries. It's actually not correct. They are invertible if you take boundary conditions into account. And using this, we were able to, well, I will stop here, but anyway, we were able to solve some kind of a problem in hydrogen physics that has to do with with magnetic monopoles, in which actually the magnetic monopoles can be understood in terms of these virtual degrees of freedom. So it's all about entanglement. Okay, this entanglement degrees of freedom are actually the defects in your quantum field theory. But I think I'm over time. I will stop here. Thanks.
Many thanks for the amazing talk. So do we have questions? Can you say something about the correspondence? Is that PhD and topological phases?
Yes. So the fact that topological phase of matter in 2 dimensions, like the most famous one is the toric code, has one of these virtual symmetries. That means that if you put this on a torus, you actually have different ground states. That means that there is something like symmetry breaking going on. A topological phase is symmetry breaking, but it's symmetry breaking in a very specific way. The ground state degeneracy depends on the genus of the surface on which the theory is defined. Okay. And how do you understand these different symmetries? It's because these loops, of course, if I can of these symmetries, these MPO symmetries are symmetries, but if I wind them around the torus, I cannot contract them to a point. And this is how you generate the different orthogonal states. But that's why these NPO symmetries are completely central to understand the general ground state subspaces in these systems. And it turns out that this error correcting codes are in one-to-one correspondence with these topological phase of matter, because these topological phase of matter have the property that all reduced density matrices, at least the local ones, are completely indistinguishable for all these different ground states. Why is this? Because these different ground states are related to each other by one of these loops. But if you calculate a reduced density matrix here, and imagine that there was a loop going through, this loop can be moved. And therefore, you cannot see it. You can put it basically very far. You will never be able to see this in your local reduced density matrices. And this is the exact property that you need for an error correcting code, that you have orthogonal states that nevertheless have the same local marginals. And that's why somehow these things, well, there's more properties, but all these properties turn out to be realizable in terms of these transfer codes, or in terms of these symmetries. It's all about symmetries. Topological order is about symmetry breaking. And this is very much compatible with what I said. Whatever you have a theory that is a certain, that has a certain phase, then it's actually dual to a theory where all the symmetries are broken. Yeah, this, well, I didn't talk about this, but there's a 2-dimensional version of all this, and this turns out to be realizable in terms of papers. Okay, something like a generalization of an MPO to 2 dimensions. Okay, this is effectively some object here that has both legs sticking in and outside of the blackboard, and this is the 2D version of this. And this is what will need to understand all this, well, 2-dimensional physics.
More questions? So I might have another one. I'm not an expert at all, so that may be a stupid question. But you talked about no-go theorems for sublinear quantum circuits regarding the transitioning from one Hamiltonian to another.
Yeah.
So from this statement, can you obtain anything about adiabatic quantum computing, any no-go theorems, something like this?
Well,
because they're transitioning from one ground state to another kind of, right?
Yeah, indeed. Well, but so what you can prove, of course, is that if you're interested in to go from one phase, like a product state, to a topological phase, the gap will actually, well, you have to, we know that the gap will close, like 1 over the system size, and then, of course, you will have to go very slowly. That means that the depth of your quantum circuit will be linear in the system size. And that's okay. If you have a quantum circuit at the depth that is linear in the system size, you can go from one phase to the other one. But like one of these topological phases of matter, you cannot prepare with a quantum circuit that is sublinear. And that you can actually rigorously prove using the tools of tensor networks, but actually of Lie problems and bonds, all these things, you can put them together to show that indeed I cannot prepare a toric code ground state by a quantum circuit, starting with the product state and acting with a quantum circuit that has a depth. It's not the number of gates, no, it's the depth of the quantum circuit that is sublinear. That turns out to be the right way of characterizing phases.
More questions? Not okay.
Yeah. And a question. So you discussed a lot about representability, but the fact that tensor networks are a very good way of encoding quantum states. And you said that, for example, traps or arbitrary geometries can be contracted efficiently at the beginning of a talk. I found that it's still a, let's say, open problem with a lot of progress that is done with belief propagation or something. But I would like to ask you, a recent line of work is going into not contracting exactly the sensors, like sampling, for example, relying on sample-based sampling. What do you think about those? Like, do you break something here? Do you...
No, but okay, so your question consists of two parts. So indeed, so in principle, if you take a random tensor network, it could be NP hard to find to contract this. Okay, to actually, it could be very hard to find this. But in practice, certainly in condensed matter situations or high energy situations, we are interested in translation invariant systems. So it doesn't even make sense to think about NP completeness if you don't have something where the number of parameters scales with the system size, because the system size is just there's not you have this if you have a translation invariant Hamiltonian, you just have to say, okay, this is the Hamiltonian, and this is basically, it doesn't matter what the system size is. So there's no way in which you can think about NP hard problems when kind of contracting translation invariant tensor networks. And it turns out that actually for these ones, indeed, all the methods that we have seem to work very well. Okay, so it's still a very big cost, but somehow there is a polynomial scaling for contracting to the tensor networks. Which not said, the cost is high, and by sampling, you can actually reduce this cost very considerably. And indeed, somehow these new sampling algorithms that use Monte Carlo sampling, you just sort of having to contract a 2D, like a two-layer version of bra and the cat together. You just sample one of these layers, contract these, turn out to have a much less cost and seem to work very well for particular systems. Although the jury is still out whether it's really kind of, because then you completely break this translation invariance. So it could be that every one of these samples that you have is actually hard to contract. Because now you have randomness. Now you have like an extensive number of parameters, because you say this is up, this is down, this is up. All these spins are different. And now you have to contract tensor networks that actually have a number of parameters that scales with the system size. And so the jury is still out whether actually in practice this will work better than immediately using these translation invariant methods. But yeah, but there's lots of work being done there, and all these approaches seem to point to the direction that indeed we just have to put more computation power and we will be able to solve all these problems. So there's no exponential scaling. You're really, all these tensor network methods, both in 1 and 2 and 3D, actually, they are able to circumvent this exponential wall and reduce the problem from exponential to polynomial complexity.
Okay, so let's thank the speaker again. Now the next talk is going to be online.
Stefano, ci senti?
Sì. Condivido.
Stefano,
Io vi sento. Jacopo?
Stefano, non ti sentiamo.
Mm. Aspetta.
Prova ora?
Ora mi sentite? Eh, Mi sentite?
Yes.
Io.